Convolutional neural networks have gained popularity as they are particularly effective for image analysis and processing, which has made them indispensable in various applications such as computer vision, facial recognition, and image classification. Their architecture consists of layers that can capture hierarchical patterns in the data. For example, a first layer might recognize edges, a second layer could identify simple shapes from those edges, and deeper layers might detect more complex objects. In each layer of the network, filters are used that traverse the image to detect specific features. We might think, for example, of edges or textures. These filters, as they move over the image, capture the positions where these important patterns for our task are found, helping the network to understand and learn efficiently. Returning to the filters, an example would be one that detects vertical lines. When used on an image, it creates a mask that highlights these patterns. Using this mask over the original image, we see how the features detected by the filter are more pronounced, clearly differentiating from other elements present in the image. We can see then how this architecture can be really useful for tasks related to images. A good example is semantic segmentation. We will see this much clearer with an example. Imagine we have a video recorded by a car's camera. Using convolutional neural networks, we can train a model that is capable of differentiating trees, people, cars, and buildings. For this, we will employ a network with an architecture based on convolutional networks known as U-Net. This type of network is especially effective for this task. Its architecture is notable for its ability to compress and then decompress the image during the learning process, which allows the model to capture and reconstruct essential details within each frame of the video, facilitating the precise identification and classification of different elements. To construct the U-Net, we will use blocks called double-conv, responsible for performing convolution and normalization operations. First, we extract the features from the image and then normalize them to improve the stability and speed of training. Each of these blocks will repeat this process twice. Next, we use this block to generate another called down, which contains the double-conv block and a maxpool operation, which summarizes the data by only retaining the maximum value, also reducing the spatial resolution. We will repeat a similar process to construct the up block, where instead of reducing, we increase the spatial resolution of the features, ensuring that the model can recover details and integrate contextual information. Now all that remains is to define the output function, which will be responsible for adjusting the data dimensionality for the final analysis, in our case, semantic segmentation. Finally, using all these blocks, we assemble our model and train it with hundreds of images. Once the process has finished, we have used it to process a video. In it, we can see how vegetation, buildings, people, and other cars are automatically detected by our model.